This video is the penultimate video in my series of videos on Edmund Landau's Foundations of Analysis. In this video I'm going to be going through most of the section on real numbers from Landau's book, with the exception of Dedekind's fundamental theorem, which I'm going to be making a separate video on at a later date. In the previous video we saw how the integers can be replaced with integral cuts, and these subsequently became known themselves as integers, and the rational numbers were replaced by rational cuts, and again these subsequently became our new rational numbers. Shortly in this video I'm going to be going through, in a kind of informal way, the definition of real numbers. However, the name real numbers is used here quite suggestively, and I suppose in anticipation of the kind of thing that we're going to show that we've actually created. At this stage we don't actually know that the real numbers that we've created and defined here behave in the way that we expect. In other words, when we compare the real numbers as defined in this video with our intuitive notion of real numbers. Most of the hard work admittedly has already been done at this stage regarding these real numbers through the theory that we developed relating to cuts. The cuts will be renamed positive numbers, and these cuts themselves form a kind of continuum structure. But in order that we have something that more closely resembles our usual notion of real number, we need to introduce the negative numbers, and we need to introduce a number that we call zero as well. The theorems themselves in this section are not really very challenging in their contents. They often state very simple and quite familiar properties of real numbers that we're fully familiar with. The difficulty for me personally when I went through this section was to really separate what I already knew about the real numbers from what has actually been proved in the course of this book. It's easy to get ahead of yourself and start to inadvertently assume things that haven't yet been proved because they feel so natural to use. This wasn't so much of a problem with cuts because they have a genuinely different feel, in my opinion, so there's less chance that you're going to get too ahead of yourself. Sometimes it can be a bit of a slog through parts of this section, again not because of the difficulty of the theorems but because of the definitions given. It means that the proofs often amount to separately going through every single possible individual case and showing that a certain property holds in each case. For example, minus a plus b is equal to minus a plus minus b we would need to prove this in several different cases. So in this video I'm going to occasionally miss out some theorems. For example, theorem 168 is one that I know that I'm going to miss out, and this is really to save time and make sure that the video doesn't get too excessively long. Some of the proofs are long, but they're not difficult, just very long. So if a theorem's missed out, then it might be because it's kind of trivial, and although it's necessary in the big picture, it doesn't really cause too much disruption to the overall understanding and flow for me to miss it out. So I don't intend to go into as much detail with this section as I have with previous sections, particularly cuts. The theorems that I go through are more to give an idea of the types of approaches that Landau uses, but typically the proofs are relatively straightforward for the theorems in this section. So let's get started with the definition of the real numbers. So let's take a look now at the definition of real numbers. So I'm going to go through this in kind of an informal way, rather than just writing it out word for word as it's presented in the book. I'm just going to go through in a more informal way. As I said in the introduction to this video, the name real numbers here is a bit anticipatory. Just because we say these are the real numbers, yes, okay, for sure they're the real numbers in this particular context, but it doesn't mean that they automatically have all of the properties that we expect real numbers to have from our intuitive notion of the real numbers. So that's what this section is really intended to show, that the real numbers that we define here in a second actually do roughly coincide with our mental intuitive image of the real numbers. So the real numbers, we've got the cuts so far. We've got to a stage where we've replaced integers with integral cuts, rational numbers with rational cuts. These cuts we are going to continue to refer to as integers or rational numbers, whichever is applicable, but now we're going to start talking about them as positive integers, positive rational numbers, and in general, when we've got our cuts, eta, so which symbols do we use? Psi, and I think it was upsilon that we used, and all the others. We're going to call these positive real numbers. So in amongst them, we're going to have the positive integers, positive rational numbers, but we've also got these other irrational numbers as well. So in general, we're just going to refer to them as positive real numbers. And to each positive real number, we're going to define a new number, a negative number. So eta, we're going to have minus eta, we're going to have minus psi, and we're going to have minus upsilon, and whatever other symbols we use. And these are going to be called the negative real numbers. And the positive real numbers and the negative real numbers are completely separate things. There is no number that we would consider both positive and negative. So it's either a number is, if it's positive, then it cannot be negative. If it's negative, then it cannot be positive. We've got a little bit of a gap between the positive and the negative real numbers, so we're going to stick another number in there, which is called 0. And this seems to fill that gap up. And again, 0 is distinct from positive real numbers and negative real numbers. So sometimes in maybe everyday situations, we might sometimes consider 0 as to be both positive and negative. Kind of an exceptional number that seems to be both positive and negative. In the same way that we might consider a constant sequence of numbers as being both increasing and decreasing, just according to the definitions. But no, we've got a very strict separation here. 0 is distinct from positive real numbers, it's distinct from negative real numbers, and all of these categories of numbers are completely separate from one another. We will still use cuts notation. So whenever we refer to a real number using these symbols here, we're talking about a positive real number. If ever we use one of these symbols, in other words with a minus sign in front of it, we're definitely talking about a negative real number. But also we'll use uppercase Greek letters as well, if I can remember the names of them. So that's eta, psi, upsilon, zeta, etc. Sometimes we will refer to real numbers using these symbols. So if we don't necessarily want to specify whether a real number is positive or negative or 0, then we might refer to it as one or the other of these symbols, possibly other symbols as well. So what this means is that there can be a little bit of confusion, at least to start with, because if I say I've got the real number eta, just because it's written like this doesn't automatically mean that it's a positive real number, nor if I write this does it automatically mean that it's a negative real number. However, if I know that eta is a positive real number, then I can say that it must be equal to some cut, and I can refer to it using a lowercase Greek symbol. Similarly, if I know that psi is negative, then I can say that this must be equal to some negative real number, so using minus eta in this case. So I've got to be really careful how I use this notation. Also, as I was saying in the introduction, we've got to be careful that we don't get too ahead of ourselves. So even though we've got terms like positive real numbers, negative real numbers and zero, we can't take that as meaning at this stage that positive real numbers are greater than zero, that negative real numbers are less than zero, or even that positive real numbers are greater than negative real numbers, because we don't have any ordering defined yet on the real numbers. So we really are starting from scratch with this to a certain extent. So we've got to be very careful with how we treat these, at least to start with. So then we need to look at how do we talk about equality of real numbers. So let's say that we've got eta is equal to eta and psi is equal to psi. So in other words, I'm saying here that these are positive real numbers because I'm using symbols that represent strictly positive real numbers. Then this is, we've got that eta is equal to psi if and only if eta is equal to psi. And moreover, if eta equals minus eta and psi equals minus psi, then in this case we get that eta is equal to psi if and only if eta equals psi. So yes, it is. I don't mean to write any minus signs in here. It is eta equals psi because we have a way of comparing cuts of this form from what we've already seen in previous sections. We don't have a way. We can't just automatically extend that to these symbols here. So we have to define equality effectively of these cuts in terms of equality of these cuts here, and that's what's going on with this definition. Zero obviously doesn't feature in any of these. Zero is a distinct number from either of these. The next three theorems in this section in Landau's book, so I think theorems 163, 164, 165, would just show that equality of real numbers is a reflexive, symmetric, transitive relation. In other words, an equivalence relation. But they're trivial theorems. In fact, Landau doesn't even give any kind of explicit proofs of them. So that's the definition of the real numbers. The next part for us is to go through the ordering of real numbers. Let's have a look then at the ordering of real numbers. So we start off with definition 44, which is the absolute value of a real number. So this obviously depends on the specific form that our real number takes, whether it's positive real number, negative real number, or zero. So if psi is a positive real number, then it can be represented as what we would have used as cut notation previously as psi. Then the absolute value is just going to be psi, lowercase psi. If psi is equal to 0, then the absolute value is going to be equal to 0. But if psi is negative, a negative real number, then the absolute value is just going to be, let's say, the positive number that corresponds to this this negative real number, loosely speaking. Theorem 166 follows immediately from this. So the absolute value of psi is positive for all positive psi and for all negative psi. Because if you notice here, regardless of whether psi is negative or positive, the absolute value is represented by a positive real number. Remember this cut notation, or what we would have used to represent cuts previously, is now what we use to represent, from time to time at least, positive real numbers. Definition 45 is where we actually start to get to the ordering, general ordering of real numbers. So up to this point, we've only really been able to speak of ordering, if we needed to, on positive real numbers, because that's something that's positive real numbers inherit all of that stuff from all of the theory that we developed on cuts. The positive real numbers effectively being cuts. But now we're going to extend it to include 0 and negative numbers. So we're not interested in the case when xi and eta are both positive. So if xi and eta are not both positive, then xi is greater than eta if and only if either one of these cases obtains. So there's various combinations there that we've got to take into consideration. Notice that this makes sense here. This symbol, it might be tempting to think that we can just flip this symbol round and its meaning is just automatically understood. And again, this is where I keep warning about being careful not to get too far ahead of yourself. Yes, okay, in an intuitive sense, we know that if we flip that symbol round, then it means less than as opposed to greater than. But for all intents and purposes, with what we're dealing with here, this is a potentially completely different symbol with a completely different meaning. So we do have to be a little bit careful. But it's not a problem. This makes sense because we already know, like I say, what ordering looks like on positive real numbers. And with these both being absolute values, then by this theorem, they are both positive. All of the stuff that we developed relating to cuts transfers over. But definition 46 allows us to flip this symbol around, so to speak, so that we can say this xi is less than eta means that eta is greater than xi. So this is what is defined here, and then this definition allows us to just flip that notation around. Okay, so the next theorem that I'm going to go through, theorem 167, is I'm going to go through not because it's a particularly interesting theorem. It's more I want to go through it just to show how a lot of the proofs unfold in this section, where we've got to consider lots of different cases. So this is really the only time that I'm going to do this. It's going to be quite a lengthy proof, but not difficult. It's just going to be considering lots of different possible cases. So that's the next theorem that I'm going to go on to. So now we're going to look at theorem 167. This particular theorem is something that's quite familiar to us. It's quite recognisable because there's analogous theorems that come up in relation to cuts, rational numbers, etc. But it is an important theorem in a way. What it simply says is that given any two real numbers, then exactly one of these cases obtains. So either the two real numbers will be equal, or xi is going to be greater than eta, or xi is less than eta, and whichever case obtains, it excludes the possibility of the other two cases simultaneously obtaining. So the only reason that I've really decided to include this theorem in this video is not because it's a particularly interesting proof, but really to give an idea about the kinds of approaches that are typically taken in the proofs from this section in Landau's book. Once I go through this proof, probably you will be more convinced and probably understand maybe a little bit better why I've decided not to go through the proofs of too many theorems from this section. You'll be able to deduce for yourself that it would become immensely tedious if I were going to do that. Because in this case, what we're going to have to do is we're going to have to consider lots of separate individual combinations of cases. I think there's about 9 altogether that we need to consider. So I'm going to go through them as quickly as I can. There's going to be a heavy reliance on definition 43, definition 45 and definition 46. So it's worth bearing these in mind as I go through this. I'm going to be using them quite quickly. So let's have a look at the first case, which is if psi and eta are both positive, then if this is the case, we've actually got nothing to do, because in this case psi and eta would both be, we could represent them both by what we would have used for as cut notation previously, and we know that when it comes to cuts, the analogous theorem is true. So I think it's theorem 123 in Landau's book, the analogous theorem for cuts. So actually there's nothing for us to do in that case. It's pretty much it's covered already. So let's have a look if psi is positive and eta is equal to 0. So in this case, we've definitely got that psi is not equal to, or should I say, psi equal to eta does not obtain, because we know by definition 44 that 0 is distinct, it's a real number that is distinct from all positive numbers. So this situation does not hold. So psi is equal to eta does not hold. On the other hand, from definition 45, we can say that psi is greater than eta. So that does hold, and that's from definition, I'll just write 45 here. But we can also say that eta greater than psi does not hold. And this is again is from definition 45. Remember, definition 45 is an if and only if definition. So it gives conditions that kind of work in both directions. So this doesn't obtain, but notice that this is not quite of the right form, because all of these have psi on the left hand side. Here psi is on the right hand side. So I'm just going to use definition 46 to flip that inequality symbol around. It doesn't make it any more valid, but that's definition 46. That allows me to do that. So there's only one case that obtains here, and that's this one. Let's have a look now at psi positive and eta negative. So in this case, again, by definition 44, psi equals eta does not hold by definition 44, because positive numbers and negative numbers are defined to be distinct types of number. We can say that psi is greater than eta. So this is by definition 45. But we can also say that eta is greater than psi does not hold. And again, that's definition 45. But once more, the psi is on the wrong side. So I'm just going to use definition 46 to flip that around. It still doesn't hold, but that's definition 46. So once again, I'm just getting the one case that does obtain. So that's the case when psi is positive, and the other combination, various combinations of relating to eta. Let's have a look now if psi is equal to 0 and eta is positive. So in this case, again, we get that psi equals eta does not hold by definition 44. 0 is a distinct number from any positive number. And we can say that psi greater than eta does not hold by definition 45. But we can say that eta is greater than psi. So that does hold, again by definition 45. But once again, it's kind of the wrong way around, so just use definition 46, flip it around, and that's definition 46. And in this case, it is this one that holds. But we've just got the one situation. Out of the three possible, we've just got the one possible one that actually holds between these two in this case. Moving on, psi equals 0 and eta equals 0. In this case we get eta equals, psi equals eta, and that's from definition 44. Obviously 0 is equal to itself. But we can say that psi greater than eta does not hold by definition 45, because it doesn't match any of the criteria. We can also say that eta greater than psi does not hold by definition 45. Wrong way around again, flip it around using definition 46. Still doesn't hold. So all in all, we just get the one possible case that obtains here. So what are we up to? Let's have a look now at psi equals 0 and eta negative. So in this case, again, definition 44 says that equality doesn't hold. We can say that psi is greater than eta, and that's from definition 45. And we can also say that eta greater than psi does not hold, definition 45. But once more, it's kind of the wrong way around, so just flip it around using definition 46, and we're finished with that one. Once more, just the single case that obtains from there. And now we're on to negatives. So let's say that psi is negative and eta is positive. So in this case, definition 44, equality doesn't hold. What can I say? I can say that eta is greater than psi by definition 45. Flip it around. That's that. So psi is on the correct side now. And I'll just put a bracket around that as well. And I can also say that psi greater than eta does not hold by definition 45. That should be 46. That's better. Okay, two more to go. Psi negative, eta equal to 0. Definition 44 says that equality does not hold. And what next? What next? Psi greater than eta does not hold by definition 45, but eta greater than psi does hold by definition 45. Flip it around, 46, and once more we just get the single case that obtains. So let's have a look at the last few cases now. So we need to have a look at when we've got both negative, so psi and eta are both negative. So there's the first case that I need to consider is if psi is, let's write it as this, not equal to eta, but psi is greater than eta. So from definition 45, I'd be able to say that psi, absolute value of psi is less than the absolute value of eta. So that's definition 45. But these are just dealing with positive real numbers, and all of the the ordering of positive real numbers is inherited from all of the theory that we went through on cuts. So if this inequality holds between these two positive numbers, then I can say then that this inequality does not hold. And that's from Theorem, roughly Theorem 123. Although strictly speaking, maybe this should be the other way round and the inequality symbol flipped. But anyway, so this doesn't hold, and therefore, by definition 45, eta greater than psi does not hold. So that's definition 45. Flip the inequality symbol round, and I get psi is less than eta does not hold. So that's definition 46. And just really because I'm running out of space, I'm just going to state the next two cases. I'm not actually going to go through them, but they're just as straightforward as all of the ones that I've done so far. So in this case, we would assume that psi is equal to eta, and that psi greater than eta does not hold. And in the third case, we consider that psi is not equal to eta, and also that psi greater than eta does not hold. So in this case, we'd hope to show that the other case, psi is less than eta, also doesn't hold because we've got the equality. In this case, we'd hope to show that psi is less than eta does obtain. But just for, because I don't have space to do it, I'm just going to leave that off. I think I've gone through enough of that. So hopefully you can see from this just how laborious some of the proofs can be. Not difficult, just long and laborious. So the rest of this video really is going to be a very whirlwind tour of addition and multiplication of real numbers. Dedekind's fundamental theorem, which is the kind of climax of the whole construction, I'm going to leave for a separate video because I want to make sure that I go through it in sufficient detail. But from here to the end of this section up to Dedekind's fundamental theorem, the theorems are often as laborious as the one that I've just gone through, where it's considering all different cases. But a lot of the theorems themselves, they're not really interesting. They're just really proving in a kind of formal sense what you already know. So properties that you already know, they're essential. So don't misunderstand me. Don't think that I'm saying that the theorems are not useful in some way, that they don't contribute to the whole construction of the real numbers. But they're not. I just don't feel that they're worth spending a great deal of time on in this video. If you are interested in them, then I'd recommend that you just read the book, really. So Theorem 169. Positive numbers are greater than 0, negative numbers are less than 0. So now we can actually start to talk about symbols like this, and this being a negative number in this case. But up until this point, actually, we've not been able to say that. So I've always referred to positive numbers and negative numbers, whereas ordinarily it might be tempting to write something like this when you want to somebody to infer that this is actually a negative number. We've not been able to do that actually up until this point. Definition 52 is addition of real numbers in general. Now we've already got a definition for addition in the case where the two numbers are positive. It amounts to what happens with cuts. So going back to the section on cuts, we've already got that really dealt with. So this defines addition for all of the other possible cases when we've got at least one negative number involved, or when we've got 0 involved. And as you can see, there's all sorts of separate cases to consider here. So this is what really contributes to the length of the proofs of some of the theorems. It doesn't make the proofs difficult, it just makes them quite long and tedious and a little bit boring, I guess. Definition 53 brings a meaning to this symbol in general, so minus psi. So I said right at the start when I was defining real numbers that if we see this symbol here, minus psi, we can't take that as meaning that this is a negative number. It's only if we see something like minus psi or minus eta that we're free to assume that it is a negative number that we're talking about. Whereas here psi could be positive or negative, but if we stick a minus sign in front of it, we can still make sense of it. It's just that it might be positive. So it's the old double negative kind of idea. The negative of a negative number is going to be positive. Definition 54 brings a meaning to subtraction. Subtraction of real numbers. So one real number subtract another one. It's the familiar kind of thing that to subtract a number, we can interpret that as adding a negative number. So it's all of the usual properties. And then Theorem 187, solutions to equations. So if we've got effectively a linear equation, eta plus epsilon equals psi, then we've got exactly one solution, which is epsilon equals psi minus eta. Completely analogous to what we've seen in previous sections regarding solutions to equations, except now it's relating to real numbers. So, okay, we've just got multiplication to look at. There's not very much for me to introduce with multiplication, and that will bring us to the end of this video, more or less. And then in the next video, I'll just finish everything off with Dedekind's fundamental theorem. Okay, so we can breathe a big sigh of relief as we come into the home straight, really, for this video and the construction of the real numbers. So here, just in this last little bit before I wrap up the video, I'm going to go through, just touch on multiplication. I'm not going to prove any theorems or anything like that in this section. It really is just going to be a brief, just a brief mention, really. So definition 55 formalizes really multiplication of real numbers where we've got either at least one negative number involved, or we've got at least one of the numbers equal to 0. The case where we've got two positive numbers is already accounted for in the case where in what we did when we developed all of the theory on cuts, for example. So positive real numbers, as I keep saying, are effectively what we used to call cuts. All of the theory of positive real numbers is all of the theory that's inherited from those cuts. Theorem 204 is solutions to equations. Equations of the form eta epsilon equals psi. So we've got exactly one solution. So this is completely analogous to what we saw in the case of rational numbers, in the case of cuts. Also, just going back to the multiplication, all of the usual laws of multiplication, commutativity, associativity, and distributivity are all proved in Landau's book. I'm not going to go through them here, but they are there. And then finally, definition 56. The epsilon of Theorem 204 is denoted by this symbol here, so psi divided by eta, which is exactly what we'd expect if we were to think of rearranging this equation, so to speak. And that brings us to the end of the construction, really, of the real numbers. The only thing that's left for us to do now is to prove the completeness of the real numbers. In other words, there are no gaps, no holes in the real numbers. So we do get this continuum structure that we expect the real numbers to have. That is what Dedekind's fundamental theorem will aim to prove, and that's what I'm going to go through in the next video, and then that will finish the whole construction. I'm not going to go through any more of Landau's book. Landau does, Dedekind's fundamental theorem is like the first ending of Landau's book, but then he goes on to the complex numbers, which really I'm not going to go any further than the full construction of the real numbers. So the next video will be the last one, but I want to thank you for watching this video, and I look forward to seeing you in the next video.